Alright, in this video we're going to take a quick look at the effects of fastener placement and how it contributes to the strength of a structure. In order to look at the actual effect, we're going to use one fastener in a simplified joint. So we're going to use an idealized situation in a single fastener. So in general, I'm going to have a sample board hanging off by a set amount, and then I'm going to place a weight on the end of the board. So it's going to be a static, simple loading situation. And I'm going to place one fastener either at this location or at this location. And we're trying to determine the effect of which fastener will support the most load. And then you can use that information to determine fastener placement if you had multiple fasteners. If you're in a situation where you've only got one fastener and you wanted to put it biased towards one spot or the next, you have to do this exact same thought process on any other type of loading situation. So if this board was being held at a right angle, where you're placing the fasteners has some effect. If it was being placed underneath versus on top, that's got different effects. If it's going to be placed in dynamic loading, if it's going to be racked, if it's in a frame, lots of different situations. Each one you need to think about critically, as we are with this one. So with the experiment, I have a dark line striked across here. This is going to be the point where it's going to overhang, so the samples are all going to be overhanging the same amount. And then I have one of the lines is 3/4 of an inch from the cantilevered point, and the other one is 3/4 of an inch from the edge of the board. The logic behind that is I'm trying to eliminate the distance from an edge and the effects on that. So if the wood were to split or whatever, this is 3/4 of an inch from an edge, and then when this is placed right here, this is also 3/4 of an inch from the edge on the bottom. So that is canceled out. In this case, I'm going to use what looks like a modified truss screw or a Craig screw. So it's got a flat bottom and sort of a pan head on it with the built-in washer. And then it's got a self-tapping head on it. The self-tapping head is going to reduce the strength, especially how I'm using it now, but that's just going to help lower the point at which it fails given the weights that I have. If I had a fully threaded screw, it would be able to hold more weight, but it fails in the same fashion. I've also done the test with nails. Same exact result. Changing the fastener doesn't have any effect in what we're looking for in this case. What we're looking for is where, whatever fastener you choose, where would it be most effective? Where would it contribute the most to the strength of the structure that you're looking at? So again, one final time, samples hanging off at this point. There's a static load on the outside edge. Where is the best spot to place a single fastener if you had to? So would I place it here towards the outside, or place it here towards the inside? And I'll give you a second to think about it. So you can either place it here on the outside, and then you can also place it here towards the inside. So again, I'll give you a few seconds. All right, the first sample we're going to load will be the arrangement on the outside, and we'll see how much that can hold. So the weights I have are 5, 10, and 15 pounds. So I'm going to start, I'm going to put them biased towards the edge, and I'll do that on the next sample as well. So holding on the outside, we have 5 pounds. About 10 pounds. And then we'll jump up to 15 pounds. And now we'll go to 20. So this sample failed at around 20 pounds. From the other tests that I did, it typically fails around 15 to 20 pounds. All right, now we'll take a look at the second loading arrangement. This time the fastener is placed towards what we're calling the inside or the back of the joint. So I'll start off with 5 pounds, again slightly biased towards the outside. We'll give it a second to rest. That seems okay. We'll go 10 pounds. Seems okay. We're at 15 pounds. We'll go to 20. So the other joint failed at 20 pounds. We're going to raise this up to 25 pounds. Again, it's biased towards the outside. I did hear a creak that time. We'll see what happens. And now we're at 30 pounds total. So this is actually the 4th take I've done. So this has been loaded and unloaded several times to get to this point. It still holds up just fine. The first one failed at 20 pounds. We're at 35 pounds, and this one's doing pretty well. So in general, it's safer to assume that a fastener biased towards the back is going to be able to support more weight. What we're trying to look at in a situation like this is every part of something that you design structurally is going to play into it, even down to the placement of fasteners needs to be studied and understood, because if you just place fasteners midway through, or you just place fasteners on the end and on the end, or on the front and the back of the joint, that can have an effect on the loading of the product, or the stiffness, or the total strength, or anything like that. So again, this is an idealized cantilever with a static load, but there are plenty of products that kind of undergo this stress. So from a test like this, we should see if in this situation you had a static load on the outside, you'd want to put your fasteners biased towards this half of the joint. So this could happen if you have a very narrow area in which to put the fastener, and you can't fit two in, so you would put one of them biased towards the back. You also may do 3 fasteners. We know we don't necessarily need as many fasteners towards the tip of the cantilever, so we can put 2 towards the back side, and then one of them out here towards the open side. Would also be an effective way to use this information. This is, again, a static situation, so it is a little different. And then each loading case is different. Again, if it's on the bottom versus on the top, that will affect how it's being loaded. We'll go ahead and see where this one fails. So I'm going to put a little bit more force on it. We'll go ahead and call this. So I've got these out, biased towards the outside, and I shall grab a drill. Probably not enough weight to make it fail, I would say. This is probably only another 4 or 5 pounds. We'll just go ahead and give it a good push. So that's resisting quite a bit. This is possibly a little ambitious, but we will see. Get the balance. So now it's holding the entire vise. This vise is significantly heavier. Most of those. So you can see this would hold quite a bit more weight, and the only change was the location of the fastener. So I went and weighed the vise, and it weighs about 45 pounds, so it certainly weighs more than all the weights added together, but the center of gravity of the vise may have been a little bit inside compared to the weights. So in general, I would say this was more total weight. Look at it as more of a relative difference. There was about double the weight being held by this as compared to the fastener on the inside. So the actual magnitude doesn't really matter. How you want to think about something like this is you're looking at the holding force of the screw by the distance to the fulcrum, and then in this case you're looking at the weight to its distance to the fulcrum. So if we're going to say we have the same weight in either loading case, we can wash that out. And what we're really looking at is the holding force multiplied by the distance from the fulcrum, or the lever arm that it has. So again, in this case, the fulcrum point is the overhang and the fastener is in the back. There's other arrangements where that might switch, but if the fastener has 25 pounds of total holding force and it's 2 inches away, and the same fastener is only 1 inch away, then there's going to be more holding force on the fastener that's twice as far away. So that's sort of the loading situation that's going on here. Another way to think about it is if you don't think of it as a screw and a fastener, if you think about this clamp that I was using to hold all of this down, that might be a different way to look at it. This clamp, if I had the clamp towards the middle, it wouldn't be as effective. It'd be the same exact situation where I'm putting a load on the outside of this, and if the clamp were more moved into the center point, it could teeter-totter more. If the clamp was out towards the back, it's going to be more stable. So if that helps you think about it. But in general, just thinking about something as small as fastener placement when you're designing a total structure.